So today we're going to pick up our work on the max cut problem. We've already talked about the problem. We talked about a factor 2 approximation for the problem. It is an NP-hard problem. This is a problem that people worked on for a long time and were stuck on for a long time, couldn't get anywhere past the factor 2 approximation. And then in 1994, Gomans and Williamson, working here at MIT, introduced this idea of semi-definite programming relaxations. And what I'm showing you is it's a truly beautiful result. It was just a real breakthrough in theoretical computer science. A couple of years ago, it won the 30-year Test of Time Award at the main Theoretical Computer Science Conference. They won the Fulkerson Award for this work, which is a big award in applied mathematics. And it really opened up a whole field because until then, we'd had a lot of work on linear programming relaxations, but they said, why limit yourself to linear? Let's look at the sort of broader category of relaxations. And we wrote down the relaxation last time. It's a very, very, very simple quadratic program for max cut. Yes, max over ij edges, 1 minus xi xj over 2. Whoops. Let's try again. Maximize sum over ij in E. With the constraint that xi squared equals 1. And what we saw last time was that if x's are constrained to be real numbers, then this is an exact formulation of the max cut problem because for a given edge, this term takes on the value 0 when the two x's are identical and takes on the value 1 when the two x's have opposite sign. This constrains the x's to be plus or minus 1. So this is an exact formulation of max cut as a quadratic program. But quadratic programming is NP-hard because you can formulate max cut as a quadratic program. And so Gomans-Williamson's idea was to relax to vectors. Xi. I don't need to change the formulation at all, right? This is now a dot product. And this is also a dot product. It just says that the norm of the vectors, that they're all unit vectors. Yes? And I gave you sort of a very hand-wavy argument last time for why it is that semi-definite programming can be solved in polynomial time or is tractable, right? It turns out that it can in fact be understood to be a kind of linear programming with a really weird, infinitely large set of constraints that it turns out that you can solve using the ellipsoid algorithm and other sophisticated techniques. And actually, one of the things that Gomans-Williamson's work did was kicked off a tremendous amount of interest in solving semi-definite programs efficiently, and there's been a lot of progress on that problem as well, and sort of specialized algorithms for solving semi-definite programs faster than this reduction to linear programming. So this is where we left off, that we are able to solve this problem. I said this last time, but I will re-emphasize. These are n-dimensional vectors that we're going to read out, where n is the number of constraints, right? We have one constraint for each vertex, essentially. Is the number of variables. We have one variable for each vertex. That's going to give us the rows. We make a square matrix with n rows and n columns, and then we use the Cholesky decomposition to factor that matrix into an n by n square root, which is n-dimensional vectors. So we can relax this problem and get an n-dimensional vector solution. If you try and impose a constraint, you say the vectors have to be 10-dimensional. the problem becomes NP hard again. So you can't limit the dimensionality, but as long as you're willing to go up to dimension n, you're in good shape. So now comes the interesting part, rounding, right? This is a relaxation. It is a solvable relaxation. Can we use this to generate a solution to the cut problem? Now, actually, in order to think about that general solution, I want to point out an important concept that we're going to be actually spending the rest of today's lecture on, which is that you can think of what we are doing here as creating an embedding. We are taking a graph, which is a combinatorial object, but you can imagine that it's a physical object with these, nodes and physical edges connecting them. We are embedding a graph in an n-dimensional Euclidean space. So we had a combinatorial problem, or a combinatorial thing, and we are turning it into a kind of spatial thing, which is very useful for us humans because we reason spatially. And it's also useful because, well, space has lots of interesting properties that we can take advantage of. Okay? So we're going to be talking a lot about embeddings today. And this is just the first one. And the rounding is one that takes advantage of the spatial nature of the embedding. So we've got this collection of vertices. We want to divide the vertices up into two groups in order to create a cut, right? But now that these vertices, this whole graph is embedded in a space, one way to divide up the vertices is to divide space in two, right? If you define a division of space, then each vertex is in one side of the division, and therefore that division of space defines a cut. Yes? So what might be a plausible way to divide up space? What's the most natural one you can think of? Yeah? Yeah, dividing up a space is, perhaps the most natural way to divide up space is to draw a hyperplane through, well, who knows where, but a hyperplane divides space in two, right? So it defines a cut, right? Now, you've already answered the next question. Given what class this is, how should we pick the hyperplane that we're going to use to divide up space? Well, let's pick a random hyperplane, okay? Notice that these vectors, right? We've sort of required these vectors to be unit vectors. Which means they're kind of spaced around the origin. So it's natural to put a hyperplane through the origin. So what we're really doing is just picking a random direction for the normal of the hyperplane through the origin. Okay? So that's the rounding scheme. Pick a random hyperplane through the origin, okay. I.e. a random normal direction. Okay. Now, why intuitively might this be a good way to get a cut that is large? What did our semi-definite program do? What is this constraint? Or what is this objective? The constraints just say unit vectors. But what is this objective going to try to do to the endpoints of an edge? Yes?
You want the endpoints to have small dot product, which makes the angle between them larger, more likely to be cut?
Exactly. Ideally, these will have a dot product of -1. That's the smallest it can be. But in general, I just get more value for my objective function by making the dot product as close to -1 as possible, right? Very small dot product means very large angle. Now, if there's a very large angle between a pair of points, what can you say about the hyperplane? intuitively. Yeah?
Very likely that it divides.
Exactly, right? If two points are, if two vectors are pointing in opposite directions, then every hyperplane is going to divide them, except for the probability zero event that your hyperplane actually contains those vectors, right? So, yes, intuitively at least, having vectors that are far apart is a plausible relaxation of the max cut problem. It's sort of saying I want them spaced away, and then when this random hyperplane comes in, it's probably going to cut them. So we should get a large value. So we need to formalize that. Okay? So let's talk about how we formalize it. So let's ask about given ij in E and given xi dot xj having some value, what is the probability that I and j are separated? Right? That's the question we need to answer in order to understand how well our rounding does. Right? If we know the probability that I and j are separated, we can compute the expected number of cut edges. Right? Because that's what comes out of the, right? Again, the and the expected number of cut edges will tell us the sort of the value of our approximation. Okay? To think about this, we're talking about a random normal direction. If you actually want to generate a random normal direction, the way you're going to do this, or a way to do this, is to generate a n-dimensional Gaussian vector, which is to say that each of its coordinates has the Gaussian distribution. Okay? And I'll make all of the means be 1. I don't care about the actual norm of this vector. I just care about its direction. And the important feature of this, and again, the one that corresponds to our intuition, is spherically symmetric. Okay, so a random, if you just assign n random Gaussians as the coordinates, you get a uniform direction in the n-dimensional space. Okay. Now, another thing that's interesting about these random n-dimensional Gaussians is that a change of basis doesn't change this. So, weirdly, if you generate these n random Gaussians and then you apply a change of basis, you rotate your coordinate system and read off the coordinates of the new vector in the new coordinate system, those coordinates will still have the Gaussian distribution in each coordinate. Okay? And they'll still be independent of each other as well, right? You start by generating independent Gaussian vectors. Then this change of basis does various sums, linear combinations of them. Bizarrely, the end result is still a collection of independent Gaussian vectors. Okay? So what we are going to do is change the basis such that xi and xj are in the blackboard. Because this is just going to make it easier for me to draw the pictures. Okay? Which is to say, I'm changing basis so that all the coordinates of xi and xj, aside from the first two, are 0. Okay? Okay? So I'm doing this to simplify the analysis, but the argument is this doesn't change anything in our distribution, right? We're generating a random direction. We might as well assume that we generate the random direction after picking this basis. Okay? Now, when we generate our random direction, right? A whole bunch of the directions are going to be perpendicular to the blackboard, but they don't matter for deciding whether xi and xj get separated, right? In terms of the first two coordinates, right, our direction is spherically symmetric in the first two chords. So our random hyperplane, our questions about whether we separate xi and xj, right? We're just generating a randomly oriented line through the origin, right? Right? So is this clear to everybody? Why we can just think about these particular two dimensions and why we are just going to get a random line as the projection of our random hyperplane? Okay. So given this, sorry, let me just say random angle. I'm going to need data for something else. Given this picture, what can we say is the probability that xi and xj get separated? Right? We're just picking a random angle for this line. Yes?
The angle between xi and xj divided by pi.
Exactly. So if we have an angle here of theta, then the probability that xi and xj get separated is just equal to theta divided by pi. Right? Everybody see why it's pi and not 2 pi? Yeah? Okay. Good. So now we have a basic formula for the probability of cutting this particular edge with our hyperplane. But now, how is theta related to the quantities in our semi-definite program? Yes?
Isn't it equal to the dot product for unit factor?
Well, so in terms of units, right, dot products are kind of a length, whereas theta is kind of an angle.
Cosine of the angle.
Exactly. So it turns out that the angle, theta, is just equal to the arc cosine of xi dot xj. Okay. And so the probability of separation is just that divided by pi. Okay. So the question is, how does this relate to the objective, right? The objective gives us 1 minus xi dot xj over 2 for xi and xj, right? So if we can show that these are close, then we will have shown that we have a close approximation, right? So I claim that what matters is the worst case ratio. We're interested in the minimum of the arc cosine of xi dot xj over pi divided by, sorry, let me just call this some number. What do I want to call this? Call it r. Divided by 1 minus r over 2, right? That this ratio is going to determine the quality of our approximation, right? Because if we write this ratio as alpha, right? If we can say that the arc cosine of r, or of xi dot xj over 2, which is the probability that we actually cut the edge, if we can show that that is larger than some alpha times 1 minus xi dot xj, over pi. If we can show that that is bigger than some constant times 1 minus xi dot xj over 2, right? Then sort of term by term, the probability of cutting the edge is at least an alpha fraction of the objective function on that edge. And therefore, that's true when you sum over all of the edges, right? That would imply that the expected value of the cut is at least alpha times the value of the optimum of the semi-definite program. Is that clear? Okay, so all we need to do is figure out this ratio, and that's just calculus or numerical analysis, right? You plot this one, you plot this one, and it turns out that the answer is about 0.878. Okay, not for any interesting reason, but that's just what comes out. Okay. Yeah, what's interesting is that this happens somewhere in the middle, right? When r is 0, or when r is 1 or minus 1, you actually get equality. But somewhere in the middle, you get a divergence between these two quantities. Okay, but the divergence never gets worse than 0.878, and therefore you have a 0.878 approximation for max cut, which of course is a huge improvement on the factor 2 that we had before. Any questions? Because this is the whole analysis. Right? This is a proof from the book, a really gorgeous, just a new idea, and then boom, the answer falls out. Yes?
When you refer to the optimum, the semi-definite program, did you work with real?
No, I mean the semi-definite program produces vectors, right? And so that is the optimum. But remember that optimum, right, that this is a relaxation of max cut. So the value of this optimum will be at least as large as the maximum cut. And so we achieve 0.878 times a value that is at least as large as the maximum cut value, and therefore we are at least 0.878 of the maximum cut value. Okay? That's sort of the fundamental concept of a relaxation. So that you compare your performance to the value of the relaxation, but that means that's only better than your performance against the actual optimum. Okay? All right. Now, there's a little bit more to say about this, right? What's the natural question that you ask when you see a result like this? Yeah? Can we do better? Right? And here, we actually have pretty strong evidence that the answer is no. I will say evidence. It's not a proof. Okay? So shortly after this, and partially motivated by this, somebody named Subhash Kote invented what is now known as the unique games conjecture. And this is a really confusing name for it because it is not a unique conjecture. Okay? It is a conjecture about so-called unique games. And that does not mean that it is a conjecture about just one unique game. It is a conjecture about games that have the property of being unique, which is weird. And the property of being unique is a very strange property. So sadly, this is not a natural conjecture like the axiom of choice, for example. This is just a weird combinatorial object. But he formulated this unique games conjecture, and it turns out to tie together a lot of challenging problems in theoretical computer science and in particular in approximation algorithms. And it is now known that assuming the unique James conjecture, you cannot beat this 0.878 approximation unless P equals NP. Okay? So this is an incredibly sharp result, right? This does not, like there are various results about how you can't approximate something within, better than a log n factor. This is saying exactly what the constant is that you can achieve in polynomial time, and saying that you cannot get any better constant factor. Okay? The weakness is that this is actually subject to two assumptions. One is the unique games conjecture, and the other is the assumption that P is not equal to NP. Now, at this point, I think most computer scientists don't believe that P is not equal to NP. I believe that opinion on the unique games conjecture is pretty evenly split. But there's been a lot of work on it. There's been a lot of sort of connecting it to other things. It is sort of a central piece of research right now, and a fun thing to look at. All right. Okay, so that was. And also, sorry. There's a second result which is not dependent on the unique games conjecture. Hastad proved that you can't beat 16 out of 17 if P is not equal to NP. So that gets away with the unique games conjecture and gives a somewhat worse bound. So if you don't assume the unique games conjecture, we don't have the same tight result, but we do know that this problem can't be arbitrarily closely approximated. Okay. So this was as I said, a really big breakthrough in 1994 and has led to several decades of exciting research. I will mention a related problem. Graph coloring, for which this result gave new insight and new algorithms. Okay, and it's not really surprising. If you think about graph coloring, this is the problem of coloring the vertices of a graph so that the edges don't have their end. So no edge has two endpoints with the same color. Yes. If you think about it, that is just another way of saying I want to partition the vertices into groups so that every edge crosses between two different groups in the partition, right? Which is to say, I want to create a partition that cuts all of the edges. But it's a partition into more than two groups, right? So if you're trying to three-color a graph, you're trying to break the vertices into three groups such that all of the edges are cut by that partition into three. Okay? So the graph coloring problem is just asking for a perfect cut when you divide into multiple groups. And so it's natural to associate this with the max cut problem. And in fact, there's an even tighter relationship. There's something known as cut covering. how many pairwise cuts do you need to use so that every edge is cut by one of those? And it turns out that the cut covering number is just the log of the graph coloring number, which is called the chromatic number. So there is this tight connection between max cut and graph coloring. And it turns out that you can also get some nice approximation algorithms by leveraging this approach. Let's focus on 3 coloring. Okay. We want to pick 3 colors so that all of the edges are cut. Let's try and come up with a semi-definite program that relaxes this goal. Okay. So in max cut, we're trying to maximize a sum of kind of contributions from all of the individual edges, right? But in graph coloring, we're trying to cut every single edge, right? So what sort of change in the semi-definite program do you think would reflect that instead of just trying to sum the contributions of edges, we want to cut each edge separately? Yes?
Maybe like if you sum over the edges, like some value, they have to sum to 0.
If you make some value for the edges sum to 0, that means some edges are going to have a large value and some are going to have a small value. How does that relate to cuts or to coloring? Like, again, coloring, cuts, they're sort of related. Right? So remember, the intuition here was that we were trying to get a large cut, which means that we were trying to get a lot of the edges to be far apart from each other, to have endpoints that were far apart from each other, right? If instead we're trying to do a graph coloring, what might we want to do in the vector world? Well, we kind of want every edge to be cut, right? In vector language, that's saying we want every edge to have its endpoints far apart, instead of making the sum of distances between endpoints be large, right? So I can define what is called a vector 3 coloring. Where I try to make every pair of vertices, every pair of edge endpoints far apart. But now the question is, how far apart can I make them? So if I am using, if I need 3 different, if I'm talking about 3 coloring, so I'm dividing the vertices into 3 different groups, right? Which means I'm making vectors for 3 different kinds of vertices, right? Can I make all of them have the sort of +1, -1 that was the optimum for this cut, for this max cut problem? I can't, right? I kind of want to make 1 vector for each group, but you can't have 3 vectors that are all opposite each other, okay? But what you can do is define 3 colors that are each separated by 120 degrees. Okay. And if you do the math, that means that their dot product is -0.5. Okay. So what you can say is, I want to find a collection of vectors that are all unit vectors, but for every edge, you want xi dot xj to be smaller than -1/2. You want them to be farther apart than 120 degrees. And this becomes a relaxation of 3 coloring, because I can just use one of these vectors for each color of vertex, right? If there's a 3 coloring of the vertices, I assign the corresponding vector to each vertex, and this requirement will be solved. will be met. Yes? Yes?
Would I think you said it's more like both the negative 1 over 2? Or that's the original problem with relaxation?
You could try setting it, you could set it equal to 1 over 2, and that would make it a relaxation. But I am relaxing that relaxation even farther. I'm saying it has to be at most minus a half. I don't care if it's less. That's just going to help me by making edges even more cut. Okay? Yes?
Yeah, I'm confused. Why is the covering like equal to all?
That is a digression I don't want to go into. Like you can, it's not actually that hard to prove, but essentially, if you think of assigning numbers to the colors, right? If your chromatic number is n, then you need log n bits, and you can use each of those bits to define a cut, a two-way cut. Okay. So people buy this as a relaxation. Okay. So to round this relaxation, you need to create a coloring, right? If we use the hyperplane trick, right, that's going to cut a lot of edges, but it's also going to not cut some edges, so it won't be a coloring, right? So what you do is you pick a random hyperplane, but you shift it off the origin. So intuitively, you'll have this collection of vectors, okay? And you'll have your origin. You basically move your hyperplane off the origin in the direction of its normal, okay? And you end up, if you move it far enough, it becomes impossible or unlikely for two vectors that are far apart to both stick out of the top of this shifted hyperplane. I'm not going to prove this to you. This takes a lot more math and doesn't really reveal anything beyond what we did with max cut. I just want to argue to you that it works. And what you can show is that you're going to get a whole bunch of vertices that are not connected by any edge, which means that they're an independent set. Okay? And an independent set is something that you can give one color to. So you peel off that collection of vertices, you give it one color, and you recurse. Okay? And you just keep peeling off independent sets until you've colored all of the vertices. And this gives you what is currently the best known approximation algorithm for graph coloring. It's not very good, but it's like n to the 3/14 or something, but it's the best we can do. Did they steal all the, oh, there are the erasers. All right, so that was a little taste of semi-definite programming and also an introduction to embeddings. I'm going to spend the rest of the lecture doing more embeddings for more approximation algorithms. But we're actually going to return to linear programming as our embedding tool. There's a lot more fun that you can have with semi-definite programming, a lot more algorithms, a lot more problems that are solved using it, but I want to show you some other insights that you can get from different kinds of embeddings. But let's take a break first, because this is a good pause point, and then we will start looking at what's called the ratio cut problem and balanced graph separators. All right, so before getting back to the class content, let's discuss some logistics. It is 2 weeks until Thanksgiving, which means that next Wednesday I'll hand out the last problem set. After Thanksgiving, I'm not planning to lecture because you will have your projects to work on, and because we've already done more lectures than normal class does. If there turns out to be a really interesting topic that somebody would like to hear about in randomized algorithms, I might throw in an optional lecture or two. We will see. But certainly there will be no required lectures, no problem sets until the Monday, which is the day 2 days before the final day of classes. There will be a required attendance in this room, during which students will be peer editing each other's projects, and I will find out how many people are actually still taking the class. In terms of the project, submitting a project proposal was again optional this week. It will be required next week. Okay, that means you have to turn in a project proposal before Thanksgiving. This is for your own protection. Every year, I reject a couple of project proposals as being outside of the scope of the class. And so turning in your proposal is a way to verify that what you're planning to do is actually acceptable. And of course, the sooner you turn in your project proposal, the sooner you can confirm that, or if necessary, find yourself a different project. So although I have made it optional, I encourage you not to wait too long. After I finish this topic on embeddings and such, I will be spending the last few lectures talking about Markov chains and their applications in algorithms. They're pretty cool. They can be used to solve certain algorithm problems. One of their primary uses is for estimating probabilities or for counting problems, like we talked about DNF counting, and there are a variety of other counting problems that come up. One we're not going to be looking at, but we're looking at a cousin of it, is the icing model in physics, right? So computing the number or the partition function for the icing model is actually an NP-hard approximation, an NP-hard problem where there are interesting approximation algorithms, and Markov chains play a very important role there. But for today, we're going to continue with embeddings. And we are going to be looking at a collection of balanced cut problems. So let me talk a little bit about some of the motivation here. A lot of times you're trying to solve a large problem on a system of parallel processors. Each of which holds some state. You can think of an example of this as like simulating the weather, right? You create this giant mesh that represents different points on the planet, and you have the state of the weather at each point in the planet. And you have a graph of state influence. So when you're doing a weather calculation, right, the weather here in the next minute is influenced by the weather in the neighborhood, right? So nearby spots sort of influence what the next step of weather is going to be in your simulation. So you tend to have a lot of communication where neighbors exchange information. And then you use computation to update the state. Now, if you're trying to run this sort of algorithm on a large parallel or distributed system, that exchange of info is very cheap if you and your neighbor are both on the same computer, but it costs communication, network bandwidth, if you need to send your state to a neighbor that is stored on another computer. So there is this problem of taking this graph, which represents which nodes influence which other nodes, and partitioning it onto the machines that make up your server environment, right? And the goal is to minimize communication, right? You want to have very few edges crossing between different machines. Now, one easy way to do that is to just put all of your nodes on the same machine, right? Then you don't have any edges crossing. What's the downside of that approach? Yeah? Well, if I put all of the state on that machine, then that machine does know the state of all of the nodes. Well, if I'm storing all of the nodes on the same machine, then that machine has all the information about all of the node state. And so it can do the whole calculation all by itself. But what's the downside of having one machine doing all the calculation all by itself? Yeah? Yeah, it has to do all the work, right? All of these other machines are sitting idle and not contributing to the computation. And so it's going to take you a lot longer to run it, right? So putting all of the nodes on one machine is great for communication, but kills your CPU, right? You don't have enough processing power to do all the state update. You really want to distribute the work over all of the machines so that all of their CPUs can be working at the same time and getting your state updates. But now you have to pay in communication, right? So what sort of partition is going to be a good partition? Let's consider the simple case of just having two machines, right? So if you have two machines, then any division of the nodes is a cut, right? And the amount of communication that you're going to have to do is just the value of the cut that is between these two machines, right? So should we just look for a min cut as the way to divide up the work on the two machines? I see shaking heads. Why is a min cut not a good idea? I mean, min cuts are the best problem in the world, so why not use it? Yeah?
There's a trade-off between like the communication cost and the work assigned to each processor. So like a min cut might have like a lot of work on one machine and a lot of work.
Exactly. We saw actually in our analysis of min cut, we talked about how sometimes the min cut just puts one vertex on one side and everything else on the other side. And if you do that for one of these distributed computations, then one of your machines has essentially no work to do. It has one node, but that's basically nothing. And so you still are making all of the work happen on the other machine. So what you really want is a balanced cut, right? You want a minimum balanced cut. Which is to say, ideally, you would like to have the same number of vertices on both sides. So this is known as graph bisection, which is the min cut that divides you into n over 2 by n over 2 vertices. Okay. Now, graph bisection is that's a very strict requirement that it be exactly n over 2 and n over 2. So you can also talk about a B-balanced separator, which is where you have at least Bn vertices on each side. Okay. So B is some number less than 1. So you might have like a 1/3 balanced separator, so then it's like at worst 1/3, 2/3, and each side still has a lot of work to be done. Okay. Now, besides the communication application, There are also a lot of applications to graph separators in optimization problems. So separators are a sort of sort of a generically useful trick for graph optimization problems. Because they can be used for divide and conquer. So divide and conquer is one of our canonical paradigms for solving algorithmic problems. And graph separators let you apply that paradigm, particularly in the context of approximation algorithms. You take some graph, and you find a cut of the graph. You then solve each half of the graph recursively. But since you weren't paying attention to the other half, you're going to get it wrong at the spots where the two pieces connect. So you then have to sort of patch your solution where the two graphs meet. And that leads to approximation error. I'll show you an example of this in just a minute. Okay. So you get some error caused by the patching process. Okay. But if you can ensure that most of the value that you're trying to optimize is in the two pieces, then you can argue that you don't introduce a lot of error in the patching step, and you still end up with a good approximation. Okay. But this patching work happens at each level of the divide and conquer, right? Each level of the divide and conquer is you're creating this tree of subproblems, and at each level of the tree, you've got the whole graph split up in the subproblems. And so there's a bunch of patching work. You're basically patching the whole graph together at each level of the recurrence. And that means that your approximation error is going to be determined by the depth of the recurrence, by the depth of this tree, times the patching cost at a single level. And that means you want to keep the tree shallow. How do you keep the tree shallow? Well, you need a balanced partition, right? If you can make sure that each of the two sides is only a constant fraction of the whole, then you know that the depth of this recursive divide and conquer is going to be log n, and so you're only going to pay a log n factor in your approximation error. So let me make that concrete with a specific example, which is not actually, it's not a randomized algorithm, but it's an easy one to see. There's a problem known as min-cut linear arrangement, which comes from VLSI. It's another sort of layout problem. The idea is that you're given a graph, and you want to arrange this graph on the number line. Basically, each vertex has to be placed somewhere on the line. Now, these represent components in your VLSI problem, and of course the edges represent wires that are connecting different components. Okay. But as we discussed, when you're doing VLSI, you put the wires in these channels which have limited capacity. So what you want to do in this linear arrangement problem is minimize the congestion of the channel. You want to put as few wires as possible into the channel. And if you think about it, because we've lined up all of the nodes on a line, the number of wires in the channel at each spot can just be found by drawing a vertical line at that spot. Yes? And so you want to minimize the number of edges crossing the worst vertical line, because that determines the capacity of wires that your channel needs. Is that problem clear? All right. So here's how we solve it using this divide and conquer paradigm. Okay. If we go halfway down the wire, right, so that there are n over 2 vertices on each side of the line, right, then the vertical line that we draw here creates a bisection of the graph, right, because it puts 2 vertices, it puts n over 2 vertices on each side. And that tells us that the optimum of the min-cut linear arrangement is no worse than the value of this, is more than the value of this graph bisection, right? So the graph bisection gives you one of the vertical lines that you have to be worried about. There may be a worse value somewhere else, but it's immediately clear that the optimum bisection value is less than or equal to the optimum min-cut linear arrangement. Okay? So if you imagine finding the optimum bisection, and then, which divides the graph into 2 graphs of size n over 2, and then recursing, okay. I'm rushing through this because it's a deterministic algorithm, so it's not interesting, right? It's just a motivation for what we're going to be doing. If you then recurse, you know that the number of wires that's going to cross from the left side to the right side is just equal to that bisection, right? And so the worst cut, sorry, how do I want to say this? Yeah, the worst cut on the left-hand side has some edges, and sorry, this is the worst vertical cut caused by these lines. The worst vertical cut on the left hand has some edges entirely on the left, and some that cross to the right. Okay. But the number of edges that cross to the right is just equal to the bisection value, or is at most the bisection that we found. Okay, because they have to cross the middle point. Okay. So what that tells us is that the overall value of the min-cut linear arrangement is going to be either sort of the worst, is going to be at most the worst cut on the left-hand side plus the graph bisection, or else the worst cut on the right-hand side plus the graph bisection. Yes? Which means that overall, right, the value we find is at most the worst recursion on the left-hand side or the right-hand side, plus the value of the bisection. And so if you apply this argument recursively, you find out that you can construct a min-cut linear arrangement whose value is at most order log n times the value of the graph bisection using this simple divide and conquer procedure. So this is just one of many examples of where where finding a good bisection is a useful step towards optimizing whatever it is that you want to optimize. Okay? So hopefully that's enough for motivation why we might be interested in graph bisection. Now, I said bisection is hard. Bisection is actually NP hard. And so is graph separator. But if you think about it, if we can approximate the bisector or approximate the separator, we can use the approximate bisector instead of the optimal bisector in this sort of recursion. And then our performance is going to be worsened by whatever the approximation factor is that we achieve for the graph bisection. Okay? All right. Almost done with motivation now. But there's one more step I'm going to take to look at the problem, to derive the problem that we actually want to solve. So bisection says exactly n over 2 on each side. Separator says, 1/3, 2/3 is close, but it still puts a hard limit on having a lot of vertices on each side. So I'm going to introduce one more problem, which is called the ratio cut problem. This is a problem where we want to find the cut that minimizes the ratio. Let's call this cut S and T. Have an S side and a T side. We want to minimize the number of edges crossing the cut divided by the product of the number of edges, divided by the number of edges that could, or possible, the number of pairs that are looking at each other across the cut. Okay? So notice that if we have a cut ST, S times T is the number of edges that would be crossing in the complete graph, right? It's the number of possible edges that a graph could have crossing the cut. And this is the number of edges that the graph actually has crossing the cut. Okay. This could also be thought of as just the size of S. No, it's not. It's the size of S cross T. Okay. So I will show you that this is a sort of softer version of the balanced cut problem, but it's one that is just as useful, or that can be sort of transformed into a separator. Okay. The claim is that if you have a ratio cut algorithm, you can use it to build a separator algorithm. Okay. In particular, the claim is, this is, by the way, known as the sparsest cut problem, as well as the ratio cut problem. Because again, it's sort of looking at the density of edges crossing between the two sides compared to how many could be crossing between the two sides. Okay. So the claim is that if you have a ratio cut algorithm, you can find a separator that is not too much worse. In particular, the claim is, suppose that your bisection optimum is B. Then given a ratio cut algorithm, can be used to find a 1/3, 2/3 separator with order B log n edges crossing. Okay? So if you can solve ratio cut or sparsest cut, then you can find a separator that is nearly as good as the best bisection. And since I first made this statement, there's actually been additional work that has shown that you can find a bisection that's about this good as well. But I'm not going to show you that. It's a lot more work. Okay? What I'm trying to give you here is a sense that these problems are all intimately related to each other. Okay? How do you do it? Well, you find the sparsest cut, because that's what you can do. Okay. And you remove the smaller side. And you repeat this until you have removed n over 3 vertices. And the claim is that this gives you a separator of the desired characteristics. Okay. And why is this good? Why does it work? Well, during this procedure, okay, we still have at least 2/3 n vertices that have not been removed. Right? Because we stop when we've removed n over 3 vertices. Okay. Let's consider what remains of the optimum bisection. Okay. This optimum bisection of B edges, right? It divides the graph into two groups of size n over 2. But we've taken some vertices away, but the vertices that remain are still divided into two groups, and neither group can have more than n over 2 vertices in it, because we started with n over 2 vertices in each group, right? So it divides the remaining vertices into two groups of less than n over 2 vertices. But if each of the groups has at most n over 2 vertices, but our total is more than 2/3 n, that means that each group has at least n over 6 vertices remaining. Okay, 2/3 n minus n over 2. Okay. So what can we say about the sparsest cut? Or sorry, the value of the ratio for this partition is at most, well, the number of edges crossing the bisection, right, divided by the product of the two sides. Now, I've just told you that each of the two sides is at least n over 6, right? And if one of the sides is n over 6, then the other side is n over 2, right? So that means that this in total, right, this is more than n over 6, and this is more than n over 6, which means that the ratio is less than, whatever, 36b divided by n squared. So the fact that you have a good bisection and that you have not yet taken away a lot of vertices means that you have a ratio of 36b divided by n squared in the optimum ratio cut that you find. Okay. Now, let's think again about this ratio, right? So we are dividing the graph into two pieces. Let's say S is the smaller piece. Okay. And this is less than this target quantity here. Where'd I go? Sorry, I got ahead of myself and I have to catch up. Yeah, so we've got a smaller side and a larger side. And because of where we're working, the larger side is always is always omega of n, right? We're only taking away, we're only doing this while the graph remains big, and we're finding two pieces, and so one of the two pieces has at least has omega of n vertices in it, which means that in terms of this ratio, we might as well think of this larger quantity as theta of n. And I'm going to move that to the numerator. Okay. So we have a specific number divided by the number of vertices on the smaller side that we're taking away. Okay. And so what this tells us is that every time we remove a certain number of vertices, the number of edges that we remove is proportionate to the number of vertices that we removed. And this is the proportion factor, which means that at the end, after we have removed all of the vertices on our smaller side, the total number of edges that we have taken off is not large because it was never very large in any one step. I'm going to fill this in a little bit more detail on Monday because I want to get past this motivation, at least show you one interesting step towards solving this problem. So let's finish with a baby step, which is ST min cut. So on Monday, we're going to work out this whole sparsest cut approximation, but let me show you how we use the same techniques to get a good algorithm for ST min cut using this embedding idea. So I'm going to give you an LP relaxation for ST min cut. As with our various cut problems, I'm going to have a indicator variable for each vertex. ZV equals 0 or 1, depending on which side of the cut, of the ST cut you're on. And I'm going to have an indicator variable YUV, which is equal to 1 if edge UV is cut. Okay. And my linear program is just going to be to try to minimize the number of minimize the cut edges. Okay. With the constraint that these are indicator variables. I am also going to require that S be on the left side of the cut and that T be on the right side of the cut. And I'm going to add one interesting constraint. which is that for edge UV, we are going to require that the indicator variable for W, sorry, for V, is less than or equal to the indicator variable for U plus YUV. Okay? And this is the only sort of interesting questionable part of this linear program, right? All of these constraints are the obvious ones. Indicator variables for which side you're on and indicator variables for whether an edge is cut. What does this constraint mean? Yeah? Roughly yes. But the other way around. This is saying that if I want V to be on the opposite side of U, of the cut from U, then I have to cut edge UV, right? So if I haven't cut edge UV, which means that YUV is 0, then ZV cannot be 1 while ZU is 0. Yes? Okay, so you can't move V to the other side without cutting UV. Okay, so that is what this means when you think about it in terms of indicator variables. But